Geometry Unit 6, Section 3. The previous two videos were on different ways to dilate images. And that's what the title of this chapter is, Dilations. So we're seeing our first taste of making triangles bigger and smaller and figures like that. And the first video is about scale drawings, where we can extend the lengths of a side to make it a scale image, or the ratio method in the previous, where I could have a center that I'm going to use for the dilation, and the distance to the center I could manipulate that to make it an image twice the length, or half the length, as we saw here. And the two important things of these dilations and scale drawings mentioned in the first video are that the corresponding angles are equal in measure. They are congruent. Corresponding angles did not change, and that's also what produced a lot of parallel lines. And then the corresponding lengths are proportional. That's what we're really going to focus in on this next video here, the fact that the lengths are proportional. And it's the same proportion as what your scale is, scale factor. So what we start off here today is that triangle ADE is the scale image of ABC. And that would only work if BC were parallel to AD, and they are. So we have a scale image here, and we could think of this as, ABC is the original, and then we dilated it to form ADE. Like this would be B prime, we could also call it, and this could be C prime here. So we have two triangles, and they are scale images of each other. And so the sides are proportional. And so we have a small triangle, and we also have a large triangle. And so we could create a bunch of side proportions here. And so side AB for the small triangle, well, that corresponds to side AD for the large triangle. And side BC for the small triangle, that corresponds to side DE for the large triangle. Side AC corresponds to side AE for the large triangle. So these are all, the sides are proportionate. And if we had lengths here, like this looks like it's about 3 times the scale factor. So like if AB was 2, that means that AD would be 3 times that, it would be 6. And 2 over 6 is 1/3. If BC is 5, then DE is 15, and BC over DE is also 1/3. And this could be 10 and 30 or whatever. It's still going to be 1/3. That all of these proportions are equivalent to whatever the scale factor ratio is. And what's good about proportions, and we're going to see these down here when we start putting in numbers and what is the length, we can solve this. Like if I had a number here, here, and here, but I didn't have this number, where we could cross multiply to solve. The cross product here has to equal the cross product here. And so we see that. And the other thing about this that I want to mention is that there's other ways to write these proportions. Like let me just focus in on these two, for example. So we're talking about the left sides and the bottoms of the two triangles. Instead of doing like small to large, you could also do the two sides of the small. So like the left side of the small triangle and the bottom of the small triangle would correspond to the left side of the big triangle and the bottom of the big triangle. That could also be written like that. And you see that it's actually the same thing when you look at it in terms of cross multiplication. Like if I cross multiplied here, I have AD times BC. Well, it's the same thing here, AD times BC. And AB times DE, it's AB times DE. So you could either do your proportions as like a side of one triangle over the corresponding side of the other, or 2 sides of one triangle is equivalent to the corresponding 2 sides of another triangle. That's another way of seeing it too. So you'll see various proportions here. All right, so let's look at an example here. In the diagram, they tell us that XY is parallel to AC. And really what this is telling us is that we have a scale image. So that information is necessary for us to do this, because if these lines are not parallel, then the triangles are not what we call similar. It's not a dilation, and then there's no side proportion. So it has to be a dilation, and so lines like this would have to be parallel. So that's necessary information. But what else do they tell us? BX is 4, and BA is 5. BY is 6. And so what is the length of BC? X. And it's very likely we'll have some decimals here and stuff like that, so I'm going to just get my calculator out to do the algebra for me. But creating a proportion, it's often helpful to think small triangle over large triangle. And so just wait for this to clear out of the way. That if I do the left side of the small triangle, left side of the big triangle, come on, there we go. So left side, these are corresponding lengths. So here's my small triangle left side, my large triangle left side. So that would be 4 over 5, and that is proportionate to the right side of the triangles. The right side of the small triangle is 6. The right side of the large triangle, excuse me, is x that we don't know. And so since we know these are proportionate, we can set it up as a cross multiplication and cross product. So 4 times x is 4x, and that equals 5 times 6, 30. So then we would divide by 4 to get x equals, 30 divided by 4. I think it's 7.5, but let me just make sure. Yes, 7.5. And so 7.5 is the length of this here, 7.5. Okay, let's try another one. So here we are told that CB is parallel to DE, and these lengths are already labeled for us. We have 12 here, 6, 4, and then they want to know what is the length of CD. I'm going to label that X. Okay, so if we wanted to do small over large here, the small triangle on the left side is 12, and the large triangle, well, that would be this whole length, that would be X plus 12. So X plus 12. And on the right side, the small length is 6. The large length is this whole piece together is 10. So I could cross multiply this, be a little bit of distribution and things like that. That's not a big deal though. So 6 times x is 6x plus 6 times 12 is 60, 72. And 12 times 10, 120. I'm going to subtract 72 and divide 6. And so we get the length is 8. But there's actually another way to solve this question. And that's actually why the title is called the side splitter theorem. That we could do proportions, as I've been saying, but when it comes to a very specific case, there's another proportion you can do. And it's only this specific case. Then notice that the long side of the left triangle and the long side of the right triangle, because of the line here, CB, that this side AD is being split into 2 sections of AC and DC. So like these are the 2 sections of AD, and these are the 2 sections of AE. That side AE is being split by point B, and side AD is being split by point C. So whenever you're working with like the left and the right sides, you can do what's known as the side splitter theorem. That the left side being split, which is split into AC and CD, and the right side is, or the, I would call it the right side of this triangle, the big triangle is being split into AB and BE. And the sides being split are split proportionately. So we can do a proportion of just these 2 sides are split proportionately to these 2 sides, because both sides are being split by a point in the middle of them. Well, not in the middle, but on them. So then you could do a ratio of just 12 over x, this side split, and 6 over 4. And this proportion is going to be a little bit easier to work with than this proportion, because you don't have, to distribute and all this stuff we had up here. So we would end up with just 6 times x and 4 times 12, 48, and that's what we had here, and then we can divide and we still get the same answer. Now you can still do small over large like we did. It works both ways, but if you were working with the sides that are split by points on them, you can do what's known as the side splitter theorem here. So that's also an option. I know I'm at the 10-minute mark, but this next example is very important. So let me just do this one really quick for you. Again, we have parallel here, that this is parallel, so that's why we can do this. I want to know what is the length of x, y here. I guess I shouldn't call it x because we have an x. I'll call it a. Now, in the past, I've actually only taught the concept of doing small over large. I used to not teach the side splitter because students would sometimes use it in the wrong way. That see how this side ux is being split by v? So like I could do 2 over 1.5 for the side splitter theorem. I cannot 2 over 1.5. I cannot set that equal to 4 over a. Because notice that 4 and a are not the segments of a side being split. This is the whole length of the small triangle, and this is the whole length of the large triangle. That's not a side being split. Like this over here, Vx, that's not a side of a triangle. That's one of the sides that's being split of the large triangle. The large triangle is being split between two pieces, the 2 and the 1.5. 4 and 8 are not a side being split. So you cannot do side splitter here. You can only do side splitter if it's these two sides matched with these two sides, because this side's being split into two sections and this side's being split into two sections. So that's why it works up here, because this side was split, this side was split. But if you're working with the two parallel sides in these problems, these are not being split. You have no choice here but to do the small over large corresponding side proportions here. So this would have to be 2 over the large triangle is these together, 3.5. Whoops. And the small triangle over the large triangle A. And we can just cross multiply here. So I just, we wanted to show you side splitter theorem because it's a helpful shortcut at times, but it doesn't work every time, especially if we are, so that's 14 divided by 2, we get 7. So 14 divided by 2, a equals 7. If you're working with lengths on the parallel sides, you cannot do side splitter. Only when you're working with two sides that have a point on them that's splitting the longer side into two sections. That's when you could do side splitter here. So like we could have done side splitter here, but we'd have to figure out this length was 1, and then 6 over x, and then added these together to get this length. But because they wanted a whole length here, I think it was easier to do small over large. But here you have a choice. You could always do small over large, but sometimes, like in this case, you can do a side splitter shortcut. So sometimes it's useful, but sometimes I think it actually does more harm than good. So this is your side splitter theorem, setting up proportions and cross multiplying, solve for x. See ya.